Okay, welcome back, everyone. So we're coming to the last stretch of this conference. So first, let me welcome Ting Rei from University of Sydney. He's going to be talking about analog quantum simulation of non-adiabatic chemical dynamics.
All right. Can you guys hear me all right? I think you can. All right. Right, thanks. So I want to first thank the organizer for inviting me to this conference. So it has been wonderful to see all the exciting research that has been going on in the last week. Right, so today I will talk about our recent efforts on doing quantum simulations of chemical dynamics using an analog quantum simulation approach with a trapped ion systems. Right, so we are looking into a specific class of chemistry problems where we believe that when scaling up, it can provide quantum advantage over classical computer. Right. So today I'll talk about some of our recent works on using this approach to simulating some small-scale atomic model systems, as well as some molecular models of some real molecules. Right. Which can be shown there, which can be seen there. So the picture on the right-hand side, so there's our trapped ion system that we have. So although this picture is showing 8 ions inside these systems, but for all the things that I'll be talking about today, we are only using a single ion, to do all our simulations. All right. So this is our team. We are a theory experimental team. I'm a hardware guy, so I run the physics experiment. So we also collaborate with quantum chemists led by Professor Ivan Kassar, who is also at the University of Sydney. And we also work with Ryan McDonald, who is somewhere in the audience, over there. All right. So who were with us in Sydney, who do a lot of the theory work, the theory framework for the things that I'm talking about today. But then he has now started his own group in Dalhousie University in Canada. And we also work with Cornelius Hamper in PSI in Switzerland, as well as Juan and Joel from UC San Diego. Right. So the class of problem we are interested in is the chemistry problems where you have the breakdown of the Born-Oppenheimer approximations. Right. So we actually, hear quite a lot of times at this conference about the Born-Oppenheimer approximations, right? So essentially, it means that if you're not familiar, essentially it means that let's say we have a molecule. So it has two degree of freedoms. One is the molecular electronic levels, and the other one is the molecular vibrations, right? So the Born-Oppenheimer approximation essentially says that you can separate out these two systems, and then you can do separate calculation on each of them, and then combine them together, right? So the Born-Oppenheimer approximation is really the hallmark success of modern chemistry, because it allows the chemists to solve many problems in the last 100 years. And then, you can also use a quantum approach to solve these kind of problems. And we actually have heard quite a lot about the quantum approach, in solving chemistry, and most of them are restricted in the Born-Oppenheimer approximation regime. So most of them are only solving the molecular electronic systems, and a lot of times, people will fix a particular molecular bond, and then solve all the molecular electronic system, and then change the molecular bond, and then solve the molecular electronic system again, right? But then we know that there are many chemistry problems where you cannot make these Born-Oppenheimer approximations, right? So, for example, in this kind of strong vibronic coupling systems, so the chemists call this strong vibronic coupling systems, essentially you have a strong correlations between the molecular electronic degree of freedoms and the molecular vibrations, and you really need to solve everything as a whole, right? So, and then this kind of systems, usually happens very fast, and so this chemists call this non-adiabatic dynamics. So in this, in the figure there, so I'm putting a very simple example of this kind of strong vibronic coupling systems where we have two potential energy surfaces. So they represent the two molecular electronic levels, and plotted as a function of Q1 and Q2, and then the other nuclear motion 1 and nuclear motion 2. So when these two potential energy surfaces intersect, at this point called conical intersections, right? So things become super interesting at the conical intersections, because it serves as a funnel, okay, essentially, to allow wave packet to tunnel between these two potential energy surface very, very fast, okay? So actually, conical intersection is actually everywhere, okay? So for example, is thought to be the process that is responsible for how our eyes detect light. So, and this is the retina molecule. So when a photon comes in, so it will excite the molecule, the retina to some molecular excited levels. And then through these conical intersections, it will induce and activate these mechanical motions, which is, the retina, changing from one isomer to another isomer, right? So this is a molecular mechanical process. It's because of this process, activated by a photon, and then going through these conical intersections, that send a signal to our brain that tells that the photon has arrived, right? So, these kind of conical intersections is also, responsible for why our DNA actually can be robust against UV light. So if you think about it, right? So actually, it's quite remarkable that the rate of us, human being getting skin cancer is actually quite low, considering how much UV exposure we are getting from the sun. That's because there's a lot of conical intersection in our DNA that can rapidly dissipate the energy coming from the UV light and quickly dissipate away into a mechanical motion. It's because of these energy conversions that allows the DNA to be robust against UV light, right? So in general, this kind of strong vibrating coupled systems in the potential energy surface can look pretty funky. It can be quite complicated, right? So this is the general Hamiltonian for the vibronic coupling systems, right? So it has a couple of terms, So the first term here is the Q and P are the position and momentum operators. So this term here is essentially oscillator, right? So they represent the molecular vibrations. And then the second term here, the N and M, correspond to different molecular electronic levels, okay? So and this equation is general, so you can have many electronic levels, okay? Not just 2 or 3, it can be more. So and then there is this coupling constant C and M, and C and M can be written as a linear sum of many different terms, right? So in the first terms, essentially, it's just different molecular electronic levels are coupled together. But then, when you come to the second term here, so there's a Q here. So essentially, this is the electronic levels are coupled together through the vibrational mode, right? So this is the linear dependence terms, and then you can also have more and more terms, right? So so the chemists know how to write down these equations, okay? So this is an equation that describes the strong vibronic coupling systems, but it is very difficult to solve these equations, okay? So and this is even with state-of-the-art, classical chemistry techniques, which is the MCTDH, multi-configurational time-dependent type 3, right? So this is, from what I understand, this is the most advanced, classical chemistry technique to solve these kind of problems. So from my understanding is that the most advanced calculation these days include only about 10 electronic levels and about 15 modes. So actually it's not very, very big, right? So you don't need to go to very, very large systems, for the classical computers to be, very difficult to solve these kind of problems. Right, so the reason is pretty simple actually. When you have for each of the in each vibrations there are many Fock states. If you really want to calculate the full quantum dynamics, it becomes very challenging to keep track of that. So there is actually a review of modern physics paper talking about this. So the chemists call this diabolical conical intersections, and the conical intersection is included in this Hamiltonian here. So the term diabolical there is actually not a technical term, okay? So it just means that for the chemists, it's very hard to deal with this kind of strong vibronic coupling systems, especially the conical intersections. All right, and then in our work to make life slightly easier, so we are going to truncate at the linear term there. So we are going to simplify this problem for us. All right, so one of the key signature of conical intersections is this geometric phase. Okay, so this is in the chemistry context. So, take for example, in this simple picture, so we have two potential energy surface intersect at this point. So there is a conical intersections. So we will consider a wave packet initially in the ground state, okay, in the lower potential energy surface, and then slightly displaced away from the origin, which is where the conical intersection is located. So if you let this system evolve as a function of time, okay, if there is no geometric phase effect, okay, so this wave packet will split into two, go around the conical intersections, and then they will constructively interfere at the opposite side. Then you can retrieve this block on the opposite side, okay. But if there's a geometric phase effect, as these two packets wave packet move around the conical intersections, they'll pick out a pi phase shift between them. So when they go to the opposite side, they will have this destructive interference. Okay, there's a geometric phase interference effect. So you can, in a simple picture, you can think of this as, at least the way I look at this is, let's say, you have a molecule and then a photon coming in and activate a chemical reactions. It can produce a product ABCD, okay, with different branching ratio. So, if there is a geometric phase effect, if there is no geometric phase effect, so we have this constructive interference, which means that, the chemical reaction can go through and maybe certain product will have a higher branching ratio, okay? But there is, with a geometric phase effect, you have this disruptive interference, then the chemical reaction cannot go through, right? And so this is the kind of thing that, the chemists really care about. They want to predict what is the outcome and what's the branching ratio when a molecule going through chemical reactions. Right, so so this is a classical simulations, of these wave packet going around the conical intersections. So essentially, I'm taking this 3D picture and then collapse that into a 2D plane and see that. So this is done using solved using this Young-Taylor Hamiltonian, which is a very common Hamiltonian to use to describe the conical intersection. So it has two terms here. The first term is the harmonic oscillators, and then on the vibrational coupling terms, there are two terms here. So the first one is a poly sigma g coupled to Q1, okay, and then this is called a tuning term. So you can see this as there is a shift of the molecular electronic levels sigma g due to the coupling to mode 1, okay. And then the second term is a sigma x coupled to mode 2. So you can think of this as so chemists call this the coupling terms. You can think of this thing as there's a spin flip due to coupling to the mode 2. Okay. Right. So so this is the kind of thing that we want to see in our experiment. Okay. So the way that we do this in our trap ion simulator is the following. It's actually pretty simple. So I think Guido also talk about this. So here in this picture, we have two electronic levels, two molecular electronic levels that we want to encode. So we just use a simple our qubit to do this encoding, and then for the nuclear vibrational motions, we'll just use this mechanical motion in our ion trap, which is confined in the trap to do this encoding, right? So you can see that this is a very natural encoding, right? So this is a summary of the hardware performance of our systems. So we use a single ytterbium ion, and then we encode the qubit in the electronic hyperfine ground state, and then we use a 355 nanometer laser driving the stimulated Raman transitions to drive these to drive the spin, and then we use a single ion here, right? So for each ion there are 3 modes because it's trapping in 3D, but then so we set up in such a way that we can only talk to 2 modes. Okay, so these are the radial mode. So in the since the beginning, when we started this project, so we have made quite a lot of improvements to our hardware. So for example, we have improved our qubit coherence time from about 1 second to about 9 seconds. So this is just using the Ramsey experiment. There's no pinnacle. So I think Guido mentioned that there was a 10-minute qubit coherence time done in China. So that is with a pretty advanced dynamic decoupling. So this is without doing that, right? And then, and more importantly, we also improve our motional coherence time from about 1.5 milliseconds to ranging to about 30 to 70 milliseconds. The day-to-day operation is about 50 milliseconds, but sometimes we can measure about 70 milliseconds. And this is important, okay? And then because as you can see in the previous slide, because we are using directly the mechanical motion of the ions to do the encoding. So which means that the coherence of the motional mode in our trap ion system has to be good, right? So this is what we spent about 9 months to a year to improve this. And then during the meantime, we also upgrade our experiment systems and to make sure we can capture all the phases of the laser beams and also to be able to do a mid-circuit measurement and then to do a feedforward. I'll talk about that. All right. So I call this no free lunch. It's because it's really that we need both the coherence time of the qubit and the motional mode to be good to do this kind of experiment. Because, but most trap ion experiment usually focus more on the qubit coherence, and that's because most trap ion systems only require the motional mode to be coherent enough to do the two qubit entangling gate. But then we are simulating the time dynamic of the entire qubit and boson systems, so we really need this coherence time to be good. And also, our heating rate of this of our system is pretty low, 0.2 quanta per second, which is really helpful. Right, so I think Guido also talked about this already. So, but let me just quickly go through this. So we have a spin and boson. The boson is the motion of the trap ions. So if you set the laser frequency correctly, we can do a spin flip operations. We call this the ion trapper call this a carrier. And then if you set the laser frequency to be the qubit frequency plus the motion mode frequency, we can drive these blue sideband transitions. We flip the spin and then also add 1 quanta motions. Similarly, we can also do a red sideband transitions, flip the spin, and then subtract 1 quanta of motions, right? So if you combine the blue sideband and the red sideband together, and then we can do this as what we call a spin-dependent force. So this is, you can see that this is essentially a spin boson Hamiltonian. All right. So what we want to see is this geometric phase effect, around the conjugate intersection. So this is the circuit diagram to do that. So I will talk you through this. So we use a single qubit and then 2 motional modes, right? So in a single ion, right? So we first prepare them to the ground state, and then we apply these displacement pulse here. Okay, so this is driven by a spin-dependent force. So what this thing does is to displace the wave packet originally located in the origin. Okay, this is the ground state, suddenly displaced away from the origin. Okay, and then we will turn on this Yang-Taylor Hamiltonian, and then we will scan this as a function of time. So this is driven by 2 laser tones driving 2 spin-dependent forces. So this Hamiltonian is the same Hamiltonian as the one that I have shown previously, the Yang-Taylor Hamiltonian, but now we have moved into the interaction frame. Okay, so you can see that so far this experiment is actually pretty easy. Right, it's pretty straightforward. It's just some laser beam that you turn on. Just have to set the laser frequency. So what is challenging about this experiment is actually on the measurement part. Okay, we spend quite some time to scratch our head to come up with this scheme to do this, to see this geometric phase. After we know how to do it, things become pretty obvious, right? So this what we call the reconstruction measurements include a couple of things. So first, we have to do a mid-circuit measurement here, and then depending on the outcome of the mid-circuit measurement on the spin, okay, and then depending on the outcome of the spin, we will decide whether to proceed or not. And then this thing has to be done in such a way that it doesn't destroy the coherence of the motional mode, right? And then after that, then we will sequentially apply these 2 displacement pulse. So these are the spin-dependent displacement pulse. Essentially, what they are doing is to map the informations encoded in the 2 bosonic modes back to the qubit, and then we can make a sigma z measurement on the qubit, right? So we'll do a 2D scan on beta 1 and beta 2, okay, which is shown here. Okay, beta 1 and beta 2 here, and then so making this sigma z measurement will give us what we call the characteristic functions, okay. And then, so doing that, we will retrieve the real part of the characteristic functions. And then, so when we apply this pi/2 pulse here, we will retrieve the imaginary part of the characteristic functions. So with this, we can do a Fourier transform, okay, and then to give us the probability density as a function of Q1 and Q2. Okay, Q1 and Q2 are the position operator of the 2 motional modes. right? And then this is working in the interaction frame. Right. So with that, so essentially now we can then scan the time that we apply the Young-Taylor Hamiltonian, and then collect a bunch of data. Essentially now we can essentially take a movie of how to capture of how the wave packet evolve as a function of time. Right. So these are our experiment data. So from left to right, is time increasing, and so it matches pretty well with the theory curve. So which is quite nice. And then, so it's also that, I haven't talked about it. So, so at this point here, so the wave packet, they go to the opposite side. So, and then they have this pi phase shift, so you can see this disruptive interference. So if you keep on let the system evolve, so they'll come back to the origin, right? But then now they'll pick up an additional pi phase shift, so that at this point, they will constructively interfere again, so that we can retrieve this block, although it's slightly smaller. So, yeah, so this is so we can see this very clear geometric phase interference due to these evolving around the conical intersections. So this is quite nice because so according to my chemistry colleagues, this is a problem the chemists have been trying to solve, trying to observe since the 1950s, right? So although the chemists were able to see some kind of signature of this geometric phase effect in the real molecule when they were trying to do this using a high-speed femtosecond laser, but then it was never like a smoking gun, right? So we were able to show that in our simulators we can observe this very clear geometric phase interference. All right, so so there was so that experiment was essentially you can see it as a toy model, right? Toy model, to show that our simulator works. Oh, I should mention that this experiment you can also solve this thing using a digital quantum computer. So you need at least about 10 or 20 qubits to solve this thing. But then we are using a single ion, in the analog quantum simulators to solve these problems. Right. So the geometric phase experiment, you can see this as a toy model, and then and also to demonstrate that in the analog simulators, in principle you can extract any observable, right? Although the problem is non-trivial, okay. So you might have to be creative, to come up with a measurement scheme like what we've shown then, to extract the measurement the observable that you want to see. So, but then now, this is some new result. So we essentially reprogram our simulators now to look at some real molecule. Okay, so this is a Butatriene. So this is the minimum basis set. So the things that we are simulating are two electronic levels. So they are shown as the pinkish and the bluish color thing there. So those are the molecular electronic levels. They are pi star and pi. And then I hope you can see that. So in there, we have two vibrational mode, color coded by the red color arrow and the blue color arrow there. So this is the Hamiltonian for that. So this is the spin boson coupling Hamiltonian, the strong vibranium coupling Hamiltonian. So with this, you can plot these potential energy surface. And so the thing that we want to simulate is, consider a wave packet initially in the upper state, okay? So if you let this system evolve, okay, so this wave packet will roll down this potential energy hill. And then once they reach the conical intersections, things become very interesting. So the wave packet will split into two. Some will remain at the upper level, and then some will go to the lower level, okay? So we want to see, how much populations remain at the upper level as a function of time, okay? So these are all the parameters that we had to tune in, to do this experiment. So the circuit diagram is actually slightly simpler. So we just need to do one displacement, and then turn on this Hamiltonian, and then scan this as a function of time, and then we do a sigma z measurement on the qubit, right? So with that, we can measure this. So on the bottom axis here, so these are the time scale of this chemical dynamic happening in the real molecule. So in the femtosecond time scale, but then in our simulators, we can do this, we can apply these scaling factors to effectively slow it down so that we can slow it down to the experimental time scale, which is about millisecond, right? So, so this is what you will see, if you let this system evolve as a function of time. It's pretty interesting. So you will see some oscillations due to some coherence between the electronic and the vibrational level, right? And then, so that's the first real molecule that we simulated, and then we can also slightly reprogram our simulators now to look at a different molecule, right? So this is the Pyrazine molecule. Pyrazine is essentially like a benzene, okay? But then you replace two ends of the carbon atoms and replace that with nitrogen, right? So we also have two electronic states here, pi star and n pi star, and the two vibration mode are the ring breathing mode, and these are our plane hydrogen wave mode. It's interesting name, right? So so this is Hamiltonian, and then we just have to program this parameter here. So essentially, this parameter will change the shape and the orientation of this potential energy surface, and then yes, and I should mention that so our work rely on this parameter can be solved first, right? This can be done, using classical computer, right? Maybe some using a DFT method or some other chemistry method, of your choice. You can also use a quantum computer to come up with this number. So this will serve as the starting point, and then we will plug this number into the Hamiltonian, and then so these parameters are the static parameters. You can solve using the previous classical chemistry methods. And then our simulator is more interested in the time dynamic of the evolutions, right? Right. So and then so this is what we measure. So similarly, what we're interested here is we can roll down the potential energy here, you split into two, and then we are measuring how much population remain in the upper level. So it's actually quite interesting that so if you look at the black color curve is the theory data, right? You can see that even with this pretty simple Hamiltonian, it's just a linear vibranium coupling, you will see all this fine feature. And then these fine feature will depend on the amplitude, on the oscillation, all this kind of thing. They are all depend on all these parameters here, right? So these are the coherence due to the electronic levels and the vibrational mode, right? All right. So we can also simulate open chemical dynamics. So Guido has talked quite a lot about this. So this is we are simulating the Pyrazine molecule in the non-equilibrium dynamics. Essentially, you can think of this as we are placing the Pyrazine into a thermal bath which has an infinite temperature. So we can directly implement and simulate this Lindbladian, And the nice thing here is that we are also using a single ion here. Okay. So the trick here is that we just inject noises to simulate this vibrational heating. But then this is not just like some random noise you put into the system, right? So this has to be well calibrated. So what we do here is we inject white noise onto the motional mode frequency. Okay, so we apply this noise onto our trapping electrode centered around the mode frequency, which is about 1.5 megahertz or so. All right. So and then at this point, sometimes I'll get this question that it's not super interesting, right? So it would just the red color curve will just decay into 0.5, which is what you see, what you will expect from the usual decoherence effect. But then so this is due to this particular particular open system dynamic that we are interested in. So this is the heating by vibration heating, right? So actually, I'm quite envious about what Guido has, because Guido was showing a cooling, right? So actually, if we combine the cooling things that Guido did and the heating things that we do, we will be able to control the temperature of the bath. So which can be very interesting, because a lot of time the chemists care about what is the product of the chemical reactions at some non-zero Kelvin temperature, right? Oh, so I should say that it's like I go to tangent a little bit. So it goes to 0.5, so it's not very interesting. But I want to point out that so if you are able to simulate a thermal bath at a certain finite temperature, you will see that you can see that so the orange color one is the highest coupling to the thermal bath. You will see this oscillation effect, and then it will not go to 0.5. It will go to some other populations. So and then these are the things that the chemists care about a lot. They want to determine where is the output. All right, so recently we put out this archive paper. This is a theory framework paper to talk about how do we actually inject noises, inject dissipation into our hardware to simulate the dissipation effect that the chemists care about, right? So we can we can do this in a hardware efficient manner, so that we don't need to add quite a lot of quantum resources. We can just hacking a little bit of the trapped ion hardware to implement all the dissipative mechanism that we will need to simulate open chemical dynamic problems. All right, so this is another experiment. So one thing I quite like about doing this kind of simulation of a molecule is because we have something we can benchmark our method to, right? So, because in a real molecule, most likely you can use some spectroscopy technique to determine the fingerprint of the molecule, right? So we have that in mind, so that we implement this experiment. We come up with this scheme to essentially based on our analog quantum simulation framework, and then we use this method to use this framework to come up with a scheme to predict. In this case, the vibronic spectrum of a molecule. In this case, this is the SO2 molecule, sulfur dioxide. So, predicting spectrum is measuring the frequency, right? But then our simulator is actually doing the time dynamic simulations. But then time and frequency is just a Fourier transform of each of them. Okay, right? So this is the key insight, that we are doing spectroscopy in the time domain, and this is the circuit diagram for that. So in this principal experiment, this is a smaller, easier experiment actually. We also have a dissipation pulse, and then here we put in the Hamiltonian for the SO2 molecule, and then we scan this as a function of time, and then by doing the sigma g measurement on the qubit, we can retrieve the real part and the imaginary part of the autocorrelation function, which is this part here. And the imaginary part of the correlation function is by applying an additional pi/2 pulse here, right? So then we can combine these two data together to get a complex autocorrelation functions. All we need to do is to do a Fourier transform from this time series data. Then we can retrieve the spectrum in the frequency domain. Okay, so our data is shown as a red color curve there. And then agrees quite well with the classical simulation of this circuit diagram here. But I also want to draw your attention to this inset here. So the gray color curve is actual spectroscopy data that the chemists do in the laser lab. So they have a sample of SO2 shot in the laser beams, and then to see this gray color curve. So our experiment agrees well with that, especially for the amplitude, right? And then there are two additional observations here. The first one is that our peaks, the red color peaks, are sharper, right, compared to the gray color curve. That's because the gray color curve is performed with a sample of about 320 Kelvin. Okay, so there's some Doppler shift in that. But then our simulation is simulating near to 0 Kelvin, because we first prepare the bosonic mode to the ground state, right? So it turns out that this is echoing what I just said, what Guido's mentioned also, that for this scheme, right, it turns out that if you want to simulate a molecule at a higher temperature, you have to inject noises into into the system to simulate molecule at a higher temperature. So this is quite nice, right? So if noise injection is part of your simulation scheme, which means that your scheme is become robust against noises, right? All right, actually, how are we doing with time? 4 minutes, okay. So then maybe I'll quickly go through this and skip this guy. So in the last 2 years or so, I talked to a couple of chemists who has been studying this kind of quantum chemistry for their entire career. Sometimes they will ask me like, the one question that I'll get is, can I prepare some funky shape bosonic state, right? So because all the things that I've shown, the Butatriene, Pyrazine, and the geometric phase, they all started with this Gaussian state, right? So although we displace them slightly, but then it's still a Gaussian state. But then sometimes chemists care about the initial state to be in some funky shape, right? So I'll just quickly mention this. So this is separate work, but then we believe that the things that we do here will also address that. So essentially, we come up with an optimal control scheme to effectively create arbitrary bosonic state. So the idea here is we have this blue sideband and the red sideband interactions. We let the phases of these red sideband and blue sideband interactions to be independently adjustable and optimizable, right? So we optimize the cost functions essentially to bring initial state here after going through some phase modulation profile to go to the final state. And the final state, the bosonic state, can be the whatever state you want to create. You just need to dial in this into the numerical optimizer. So it will minimize these cost functions. So this is essentially the fidelity. And then we also add some extra term there to make things more robust. So essentially, we show that by simply adjusting the blue sideband and the red sideband phases, we can create this kind of state, right? So these are the GKP state. Maybe some of you are familiar with. So these are people are interested in using this kind of state as a hardware efficient manner to encode logical qubit, right? So on the left hand side over there is the GKP state, and then on the right hand side there is the binomial state. So I think for the bosonic state that the chemists care about will not be so funky, but then essentially showing that seeing that we can use this control scheme to create this kind of state, it gives us confidence that we will be able to create arbitrary bosonic state that can be interesting and be important for chemistry simulations. All right, I will stop here, and maybe I'll briefly mention that I think I think this analog simulation of chemistry is quite nice, but then there are still some challenges if you want to scale things out further. So the first one is how to generate an harmonic potential, because so far our simulations are using the bosonic mode in mechanical motions, so they are highly harmonic. But we know that in molecule usually it's not that harmonic. Usually it's like they are open up. So so it will be a challenge to engineer this harmonic potential. We now have some ideas of doing this, but then it remains. It will require some work to be done, and then we believe that this optimal control scheme that we show will be important for that. And it's also that so far in our demonstration we are only using a qubit to encode molecule with two molecular electronic levels, but we know that there are more electronic levels in molecule. So in our scheme, they will require using a qubit for that. All right. So so actually, I want to first list this slide up. So it's kind of nice to see that Guido also have a similar picture compared to what we have in mind in terms of scaling things up. So this is our idea. So essentially, what we want to have is at the middle ions will give us a high quality qubit, okay, and then the helper ions that will just be for us to let the system have more bosonic mode as we need. Because each time we add one ion into the system, we have 3 additional bosonic mode. Right, I'll stop here, and thank you for your attention.
So we have time for maybe one quick question.
So apart from maybe the number of like vibrational modes or other modes, what are the specific like experimental limitations or so chemistry maybe motivations that lead you to do these like choose which molecules you want to test out in these initial like experiments? Like how do you choose which molecule you want to investigate? And what are the limitations? Like it seems quite programmable.
The limitations, yeah, the limitations I think is, I think I mentioned this also, that we think that, we may need some specialized hardware for this, because I believe, it seems to me that, most of the ion trap system these days is heavily focused, developed to this QCCD architecture, which is not really suitable for this kind of work. And then it requires some work to be done to investigate, come up with maybe from ground up, like designing a specific hardware to this kind of thing. And to answer your first question, why we choose this molecule, is mostly because we want to start small first. Okay, so we choose this molecule because this is quite nice that the minimum basis set, the dominant electronic levels, and the dominant molecular vibrations is only there are only two of them, 2 electronic levels and 2 bosonic modes, right? So we want to learn what's the challenge there and show that we can do it, and then we'll go to bigger molecule, which we plan to do.
All right. Let's thank the speaker again and welcome the last speaker of the conference.